back. Next we'll continue with the images. Images are also represented by bit patterns. In its simplest form, an image is composed of a matrix of a pixels, that is picture elements. What is the definition of a pixel? A smallest addressable unit in the image, that we can call it as a pixel or picture element, where each pixel is a small dot. Small dot we are going to call it as a pictorial element. The size of the pixel depends on the resolution. For example, an image can be divided into 1000 pixels, that is 1000 cross 1000 matrix we are going to divide, or 10,000 pixels, 10,000 cross 10,000 matrix we are going to divide. In the second case, there is a better representation of the image, better resolution, but more memory is needed to store the image. Why? Because the matrix length will be more. That is why it takes more space to store the image. After an image is divided into pixels, each pixel is assigned a bit pattern. Each pixel will be assigned as a bit pattern. The size and the value of the pattern depends on the image. For example, image made up of only black and white dots. Example, a chessboard. Okay, a one bit pattern is enough to represent a pixel. For example, if it is a grayscale image, white will be represented by 1, black will be represented by 0. 1s and 0 for the grayscale image. In that also normal gray and normal gray, four different categories we are going to divide, that we can discuss later. That is, if an image is not made of a pure white and pure black pixel, we can increase the size of the bit pattern to include grayscale. Now, for example, to show 4 levels of a grayscale, we can use 2-bit patterns. How exactly? 1-bit pattern is white is represented by 1 and 0 is represented by black. Now, 2-bit representation. A black pixel can be represented by 0, 0. Pure black will be 0, 0 and pure white will be 1, 1. Now, a dark gray pixel by 0, 1. Light gray pixel by 1, 0. Like that we are going to divide for the 2-bit pattern. 2-bit pattern. Okay, I will repeat 2-bit patterns. Okay, a black pixel can be represented by 0, 0. A dark pixel can be represented by 0, 1. And a light gray pixel is represented by 1, 0. And a white pixel will be represented by 1, 1. Okay, 4 different cases. It is black, dark gray, light gray and white. There are several methods to represent color images. Okay, this is about your grayscale image, that is black and white image. Now we will pass to the color image. There are several methods to represent color images. One method is called RGB, so called because each color is made of contribution of 3 primary colors, that is red, green and blue. These are the primary colors to get a color image. The intensity of each color is measured. It will be binary values will be vary from 0 to 255. Color images will be vary from 0 to 255. Grayscale or white and black images will be represented by ones and zeros. Okay, 1 bit will be 1 and 0, 2 bit will be 1 0 0 0 0 1 1 0 1 1. Okay, like that we are going to represent for the grayscale image. But in the case of color image, we are going to start it with a 0 to 255. Okay, it's the range of a color image. And the combination, and here each color is made up of a combination of 3 primary colors, that is red, green and blue, RGB. And the intensity of each color is measured and a bit pattern is assigned to it. Another method is called YCM, that is in which a color is made of a combination of 3 other primary colors. That other 3 primary colors will be yellow, cyan and magenta. Yellow, cyan and magenta. Cyan, C-Y-A-N, it's a spelling cyan, and the magenta will be M-A-G-E-N-T-A, magenta. These are the 3 different colors combination. Okay, it will be made with respect to the YCM. It is also another method of color. Next, coming to the audio and video signals. Here audio represents, it will be refers to the recording or broadcasting of a sound or a music. Audio is by nature different form. It will be in the different form, that is text, numbers, images. It is continuous. It is not discrete. Okay, even when we are use a microphone to change voice or a music to an electric signal, okay, we create a continuous signal. Okay, these things we will discuss later in detail. Okay, how exactly we are going to differentiate continuous and discrete signal? What is a continuous signal? The signal is varying with respect to time. Okay, for example, if I am going to take a time bound will be from 0 to infinity, 0 to pi, 2 pi, 3 pi, like that it will be keep on varying. So example, sinusoidal signal. At every instant of time we have an information, means at 0 second we have an information, 1 second, 2 second, 3 second, it will be keep on continuing. It will not be having any break from one time slot to another time slot. That type of signals we can call it as a continuous signal. We already discussed these things in the for signals and system. Okay, that is the basic definition for the continuous signal. Continuous signal means it will be vary with respect to time. And what about discrete signal? Okay, at every instant of time we have an information. In between two different time slots we don't have any information. That type of signals we can call it as a discrete signal. Okay, all audio signals is analog signals, that is continuous signals. Okay, why? Because it will be vary with respect to time. Next we'll come into the video. Video, it will be refers to the recording or broadcasting of a picture or a movie. Video can either be produced as a continuous entity. Example, it's a TV camera. Okay, or it can be a combination of images. It will be combination of an images, each a discrete entity arranged to convey the idea of motion. Okay, we will have learn more about this in the future. Video means it's a combination of both images. It will be moving. Okay, we are going to take the combination of images and we are going to move around the with respect to time. Okay, that we can call it as a differentiate between your picture as well as a video. Next, coming to the communication between two devices can be different data flow. Okay, what are the different data flow we are going to call? Different data flow techniques are simplex, half duplex and full duplex. Okay, what exactly data flow will be with respect to the in the first case we will transmit a data from mainframe to the monitor. Okay, what exactly the meaning of mainframe and what exactly the meaning of a monitor? Here in the second stage we are going to transmit a data from half duplex, we can call it as from one system to another system. Here third one will be full duplex, we are going to transmit a data from one system to another system. What are the rules and regulations we need to follow and what is the basic condition to transmit a data? First we'll discuss about first one, that is simplex. In simplex mode, the communication is unidirectional. We can observe the direction, unidirection from mainframe to the monitor. We can transmit data from mainframe to the monitor. We cannot transmit data from monitor to mainframe. That is why we can call it as it is a unidirectional. It's a single direction. It will be from mainframe to the monitor. As on a one-way street, it is like one-way street. Okay, only one of the two devices on a link can transmit, the other can only receive, which can be represented in the following figure. Okay, a keyboard is an example, a traditional monitor or example of a simplex device. The keyboard can only introduce an input. The monitor can only accept the output. Okay, the simplex mode can use the entire capacity of the channel to send data in one direction. Okay, this is a best example of a simplex. That is Keyboard and the monitor. Keyboard can give the inputs, monitor can accept the input. Okay, so that this is the best example for your simplex.